For Chapter 10, we're starting off with a section that just talks about sequences. So keep in mind, guys, a sequence is just a function whose domain is a subset of integer values. So probably the most familiar sequence that you've been accustomed to is the Fibonacci sequence, where we say, well, 0, 1, 1, 2, 3, 5, 8, 13. And you see pretty quickly it's a recursively defined sequence where each term is just the sum of the two previous terms. So 21 is 13 plus 8, 34 is 21 plus 13, 55 is 34 plus 31, on and on and on. So it turns out that this sequence occurs in nature quite often. But if I wanted to define this sequence, I would say the a sub nth term, so the nth term, is just equal to a sub n minus 1 plus a sub n minus 2. So in other words, the nth term is the sum of the n minus first and the n minus second term. But we use the subscripts like this to designate the terms. Now, let's look at some problems based off of that. Let's say I tell you that a sub n is a sequence defined with the formula 1 over 2n minus 1, and that it's defined for n is equal to 1, 2, 3, and so forth. Now, I'm wanting us to write out the first three terms of these sequences that are dependent upon the answer for a sub n. So it says b sub n is just a sub n plus 1. Well, if I want the first three terms of b sub n, then I want b sub 1, b sub 2, b sub 3. So I'd say, well, quite easily here, b sub 1, since it's equal to a sub n plus 1, then b sub 1 is going to equal a sub 1 plus 1, or a sub 2. If I plug a 2 into the sequence formula for a, I would see it's 1 over 2 times 2 minus 1 for the 1/3. b sub 2 is just going to equal a sub 3. You'd plug a 3 into this function, you'd have 1 over 6 minus 1 for 1/5. And then you can see, okay, yes, that denominator is going to continue to increase by 2 because of the 2n down there. My next term is going to be 1/7. b sub 3 would equal a sub 4. That'd be 1 over 2 times 4 minus 1 for 1/7. Now, what if I say c sub n is just a sub n plus 3? Then you could say, well, okay, then you're going to do the same thing as you did here, except now my first term of the sequence c is going to be the fourth term of my sequence a. So I would say c sub 1 is equal to a sub 4, which is our 1/7. And then you can see that multiple of 2 is going to continue to increase our denominator by 2 each time. So c sub 2 is 1/9, and c sub 3 is 1/11. Now, what if I say d sub n is the defined sequence where it's the sequence a sub n quantity squared? Okay, no problem. Then d1 is whatever sequence a is evaluated at 1 quantity squared. If I evaluated a at 1, I would get 1 over 2 times 1 minus 1. That's just going to be 1 over 1. Since a is 1, then d is also 1, since it's 1 squared. If I say d evaluated at 2, then it's whatever the series a is evaluated at 2, quantity squared. A evaluated at 2 is going to be 1 over 2 times 2 minus 1, 1/3. We square that to get to the sequence d, and I get my 1/9. Similarly, a sub 3 would be 1/5, and then d sub 3 is going to be that number squared for the 1/25. Now, what if I say, well, what if I let a sequence, not a series, what if I let a sequence e sub n equal 2 times a sub n minus a sub n plus 1? Okay, no problem. You just say, well, then your first term of the sequence e is going to be 2 times a sub 1. We talked about a sub 1 is going to be 1. And then minus a sub n plus 1. Well, a sub n plus 1, that would be a sub 2 in this case, and a sub 2 is going to be 1/3. So I could say, well, 2 times 1 minus 1/3. The very first term of sequence e is going to be 5/3. Now the second term of sequence e you'd say, well, it's going to be 2 times A2, which we just talked about. A sub 2 is going to be 1/3, so now I have 2 times 1/3 minus A sub 3, which is our 1/5. We'd say, well, 2 times 1/3 minus 1/5, it's going to give me 7/15. That would be the second term of this sequence E2. Third term of sequence E2, I'd say, okay, it's going to be 2 times A sub 3. A sub 3, we talked about earlier, is 1/5. So I would have 2 times 1/5. And then minus A sub n plus 1, well, that's going to be A sub 4. A sub 4 was 1/7. So I have 2 times 1/5 minus 1/7. When you do that, you might need a calculator. 2/5 minus 1/7 simplifies to be 9/35. So now you're thinking, well, that's not too bad. It's a little strange versus what we have been doing, but nothing bad. Now, let's talk about sequences involving factorials. Please remember, a factorial just means every number less than it. So, like for example, if I said, hey guys, I want to do 5 factorial, you can do a factorial in your calculator by hitting whatever number you want factorial, and then math, arrow over to probability, number 4. So 5 factorial, 120. All a factorial is that integer value times every integer less than it all the way down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. That is what a factorial is. It's used a lot in probability. Now, whenever we're doing that in context of a sequence, we'll just have to think of it in terms of how it's going to affect the problem. So I'm wanting us to look at the sequence B sub n, and yet again I want to write out the first 3 terms, where the numerator is going to be the group 2n minus 1 factorial. Well, B sub 1 then. I would say 2 times 1 minus 1, well, that's 2 minus 1. My numerator is going to be 1 factorial. My denominator, obviously, over n factorial would be 1 factorial. So we get our first term is just 1. What about our second term? Our second term, when you plug a 2 into that numerator, you would get 4 minus 1. That's going to give me a 3 factorial in the numerator. Your denominator, when you plug a 2 in, obviously a 2 factorial. So I have 3 factorial over 2 factorial. That's just going to simplify down to be 3. If I say, well, what about the third term of this sequence? You'd plug a 3 in for n in the numerator. You'd get 6 minus 1. That's going to give you a 5 factorial. Your denominator, obviously, the n factorial, 3 factorial. 5 factorial over 3 factorial ends up just being 5 times 4, which we know is 20. And just for the fun of it, I went ahead and did the fourth term of this sequence. You'd say, well, if I plugged in a 4, you get 2 times 4 is 8. 8 minus 1 is 7. Your numerator is going to be 7 factorial. Notice your numerator kept on increasing by 2 each time with a factorial because of the multiple of 2. My denominator just 4 factorial. So B sub 4, 7 factorial over 4 factorial, I know that that's just going to be 7 times 6 times 5, because then the rest would cancel out with a 4 factorial in the denominator. That's where that 210 came from. So now I can say the first 4 terms of the sequence B sub n are 1, 3, 20, and 210. Of course, this sequence would continue forever and ever and ever. Now, that leads me to this next idea here. This sequence B sub n is going to diverge. The reason it diverges is because it's not going to reach any one number. It's just going to keep on getting larger and larger and larger and larger and larger. So we say a sequence converges to L if the limit as n approaches infinity of the a sub nth term of the series is equal to L. Otherwise, we just say a sequence is divergent. So if you can tell what's happening to a sequence as it's getting extremely, extremely large, as it's going to go off to the infinite term, if the infinite term is approaching one number, it converges to that number. If it doesn't, it diverges. Now, it could diverge because it goes to infinity, or it could just diverge because you don't know what it goes to. Now, let's look at some of those. If I ask you, in all of the remaining problems, it's just, does the sequence diverge or converge? So the sequence I'm giving here, a sub n is equal to 20 minus 4 over n squared. So all I need you to do is think about what happens to this as n gets large. So I show that. Let's put a limit as n approaches infinity. We're going to have 20 minus 4 over n squared. I know 4 over n squared goes off to 0 as n gets large. So this sequence is just going to approach 20. So I would say this is a convergent sequence. It converges to 20. What about if I give the sequence a sub n is equal to 4 plus n minus 3n squared over 4n squared plus 1? This should bring back some fond memories of limits from Calc 1. Earlier in the semester, we did these algebraically. Later in the semester, we did them with L'Hopital's rule. Right now, for this one, you could even go back to pre-calculus and think about anytime the degree of the numerator and denominator is the same inside of a rational function, then the horizontal asymptote is going to be nothing more than the fraction of the leading coefficients. Numerator and denominator are both degree 2. So you'd say, well, this is going to have a horizontal asymptote that's at negative 3 over 4 because that's the coefficient, the leading coefficient of the numerator and denominator. I can see that from this very first step. Well, to show out my work, I would say, well, okay, all we have to do is take a limit as n approaches infinity of the numerator over the denominator. If I wanted to show it algebraically, what you would do is you divide by the power of n in the denominator. And so I'd say, well, okay, 4 over n squared plus n over n squared becomes 1 over n. And then 3n squared over n squared just becomes minus 3 there. My denominator, 4n squared divided by n squared is just 4, and then I divide the last term by n squared. So this is the same thing as this. This is just trying to show it out in a better format. Now, take the limit as n approaches infinity. We've went through and we've divided every single term in there by n squared, which is a legal algebraic maneuver. But now if you take the limit, we know any finite number divided by a number going to infinity is 0. So I would say in my numerator, that term 0, that term 0, clearly my numerator is just a negative 3. My denominator would be 4 plus 0, so that shows you your answer is negative 3/4. Now, do you need to go through this step if you can just look at the beginning and say, hey, that has a limiting value of negative 3/4? Absolutely not. You can just say this sequence converges to negative 3 over 4. Now let's talk about geometric sequences. A geometric sequence is just when you have obviously an exponential function in there with a base r raised to the n power. So we're going to have some constant r raised to the n power, and n is going to get larger and larger and larger. Now you could have some constant coefficient c multiplying it. The c is really not relevant to whether or not it's going to be convergent or divergent. What's relevant is what's happening to that exponential function, what's happening to that base r raised to the power of n. So in this geometric sequence, this is going to be your convergence divergence rule. If you look at the limit as n approaches infinity of any base r to the n power, and we know n is going off to infinity, well, the determining factor is whatever r is. And think about that. If r is some decimal value between 0 and 1, let's say even if it's 0.9, 0.9 to the infinite power becomes 0, because anytime you have a decimal less than 1 raised to a power greater and greater and greater, that decimal gets smaller and smaller and smaller. Just think of that. Even if r was 0.9, and let's say I raise it to the 10th power, it's already going to be small at that point. Notice it goes all the way down to 0.34. If I say 0.9 raised to the, let's do the 50th power, notice how much smaller it gets. So n is going off to infinity. Clearly, if r is any value between 0 and 1, that geometric sequence is going off towards 0. And again, c times any number going to 0, going to go to 0. The c becomes irrelevant. If r is 1, well, 1 to any power is 1. So that's the trivial case. So if your r value is 1, 1 to any power is always 1. So you'd say it's going to go off towards 1, or whatever c times 1 is, it would go off to c, depending upon what the value of c is. Now, What if r is a number greater than 1? Well, it's easy. It's going to go off towards infinity, no matter what c is. And think about that case. A number greater than 1 raised to a power, even if I did something like 1.1. 1.1 raised to the 50th, notice it's already at 117. If I did 1.1 raised to the 100th power, notice it's already over 13,000. So you say, well, gosh, if I go to the infinite power, any geometric sequence's base that has the exponential base greater than 1, it's going to go off towards infinity. Now, seeing an example of that here, we have the sequence z sub n is equal to the geometric series sequence's base is 1/3. You can say, well, okay, 1/3 to the n. When you think about what happens to that as n approaches infinity, that fraction raised to the infinite power goes off to 0. So therefore, in this case, anytime the answer is some number L, you would say it converges. So we would say, since the limiting value is 0, this one converges. The next one, it will also be convergent because I'm getting an answer here. But the reason I'm getting an answer, this is not a geometric series, clearly. I don't have a constant base to a variable exponent. This time I have variables inside roots. So whenever I'm trying to think of how best to solve this, I would ask you to either think of it just like we did this one right here, where you say, ooh, the degree of the numerator and denominator is the same, so you take the fraction of the leading coefficients. You could do the same here and say degree of the numerator is 1/2, degree of the denominator is 1/2. What's the leading coefficients in front of each of those? Clearly a 1. The sequence is going to go off towards 1. To try to show you that in another manner, what I've done here is I've said, well, I'm going to take a limit as n approaches infinity. Where did this come from based off of this? All I've done is I've divided through by the degree of n in the denominator, which is to the 1/2 power. Divide through every term in this fraction by the square root of n. Square root of n over square root of n is 1 in the numerator. Square root of n over square root of n gives me a 1 here. Then I have plus 4 over the root of n. But then it's very easy to see, okay, can I take the limit as n approaches infinity? Yeah. These two terms don't even have an n left anymore because it canceled out. This one becomes 4 over the square root of infinity. Well, the square root of infinity is still infinity. 4 divided by any infinite number goes off towards 0. So we just have 1 over 1 plus 0, limiting value of 1. And again, thus that means that sequence converges to 1. Another sequence I want to look at here, what if I have some logarithms? Anytime you have logarithms out like this, you're going to know that you should condense them down. It will be a whole lot easier to work with. This would equal, when I'm trying to think about what this series converges to, or if it converges, I would just say these two natural logs can be written as the natural log of the numerator n squared plus 4 divided by the previous log that was subtracted, n squared minus 1. Now, why do I put them inside of a limit as n approaches infinity? Because that's the whole purpose of this test. In order to determine if a sequence converges or if it diverges, you need to determine the limit as n approaches infinity. So that's what I did here. I took the limit as n approaches infinity of that condensed sequence notation, and I can easily see, hey, on the inside, you're just going to have n squared plus 4 over n squared minus 1. As n goes to infinity, that plus 4 and minus 1 become completely irrelevant. And you just say, well, you might as well just think of it as n squared over n squared, which reduces down to 1. And we know the natural log of 1 is going to go off towards 0. Now, a couple of others through here. Again, this is not a geometric sequence. What if I just have n divided by n plus n to the 1 over n? So in order to determine whether this sequence c sub n converges or diverges, I need to think about what happens as n approaches infinity. So what I've done from here to help me think about that is I've went through and I've divided by the n, since the power of n in the denominator, the degree of n in the denominator is the first power. I've divided every term in the expression by n to the first. N over n gives me a 1. N over n gives me a 1. Had to divide this term by n as well. So I have n to the 1 over n divided by n power. Now from here to here I've simplified that. You know that when you're dividing by n, you could say, well then that's going to be n to the 1 over n minus 1 power. And if it's minus 1, all I did is I got a common denominator there and said, well that's 1 minus n over n. Now whether you look at this or whether you look at this, clearly we can see the first two terms as n goes to infinity, they're just ones. But this last term, you need to understand that it's a 0. The way I would understand it's a 0 from here is because, please look at it. As n goes to infinity, the power on this n becomes extremely small, pretty much 0, becomes 1 over infinity. But you're dividing it by a larger power of n. So you'd say, oh, okay, then this numerator cancels out with the n in the denominator, and I can say this is going to be 1 over n to a power. As n goes to infinity, that term goes to 0. And again, it's just because the power on n is greater than the power on n in the numerator. If I look at this other one, I would say, well, how can I see that this n goes to 0? And I can see since n goes to infinity, this base n is going to be raised to a negative exponent. 1 minus an infinite number, that's negative infinity. Negative infinity over infinity, that's going to be a negative exponent. I can see, well, you have an infinite base raised to a negative exponent. That means 1 over infinity, which goes to 0. Excuse me. So I would have my overall limit there just goes off towards 1. This next one, a lot of people, well, in fact, all of the ones on this page tend to really confuse students because they overcomplicate the problems. If I look at the sequence b sub n, looks pretty complicated here. Shouldn't be. Here's why. When you break it apart and think about it term by term, I'm not concerned about these terms whatsoever. Why am I not concerned about them? Because think about what this term right here is. The 2 to the negative n, we know that that means 1 over 2 to the positive n. This denominator here, the 4 to the negative n, that term in the denominator, that's nothing more than 1/4 to the positive n. Well, as n goes to infinity, any fraction, we talked about this back on the first page, any fraction as that base, for a base that's going to be a fraction and n's going to infinity, we know that that term is going to go off towards 0. So anytime your base r is a number between 0 and 1, and that's raised to an infinite power, this term goes off towards 0, that term goes off towards 0. So I'm essentially adding zeros in the end of the numerator and denominator there. I'm not worried about them. So the overall limit's just going to be defined by this first portion. And what I'm wanting you to see with the first portion there is, hey, that's a polynomial function over a polynomial function. I have an n cubed in the numerator and I have an n cubed in the denominator. What's the only difference in the two? Well, the one in the numerator has a coefficient of negative 1 to the n power, whereas the one in the denominator is a 3. So I can say, yeah, okay, as this goes off towards infinity, the n cubes would end up canceling each other out. But the problem with that is this negative 1 to the n power, it could be a negative 1 if n is an odd number. It could be a positive 1 if n is an even number. So this limit's going to continue to oscillate between negative 1/3 and positive 1/3. So this is an example of a limit that's divergent, not because it goes to infinity, because this limit certainly does not go to infinity, but it diverges simply because the limit's going to two different values. It will either go to negative 1/3 or positive 1/3. This is also going to happen quite frequently whenever we have sines or cosines in the numerator that go towards negative 1 or 1. This is an example of a case where the numerator is going sometimes negative 1, sometimes positive 1, depending upon whether infinity is an even or an odd number. This last one, you'll see where the normal way that you would do a problem like this is you'd say, well, I would like to set up a fraction and use L'Hopital to try to determine whether this limit's going to infinity or some finite value. So the way that you would normally set up something like this, I'll say, well, I'm just going to leave that group in the numerator. I need to make a fraction of it, so I put an n to the negative 2 in the denominator. And then L'Hopital says that this indeterminate limit, right now, the reason it's indeterminate is because you would have the cube root of an infinite number minus infinity divided by 1 over infinity squared. You got 0 over 0. That is indeterminate. So what I'm going to try to do is I would say, well, let's take the derivative of the numerator over the derivative of the denominator. But when I did that, it's still indeterminate. I did it again, still indeterminate. It's getting worse as I tried to use L'Hopital. So instantly when I decided that that wasn't helping, I knew I needed to try another route. So I said, hey, how about I simplify algebraically before I do the L'Hopital's rule? I know L'Hopital's rule is going to be necessary in the problem. Here's what I did. I said, let's factor an n out of this group. You know the last term has an n. The first term you could factor out the cube root of n cubed and say, well, if I factored out the cube root of n cubed, my first term is going to become a 1. N cubed divided by n cubed is 1. The last term, 1 over n cubed, becomes n to the negative 3 power. Now, if I factor out that n, the n squared becomes an n cubed on the outside. And then I can say, okay, now let's try to use L'Hopital's rule. I left the part in parentheses inside my numerator, and then my denominator becomes n to the negative 3rd power. I try to take the derivative of the numerator and denominator using L'Hopital's rule because right now it's hard to see what this limit is approaching. But one use of L'Hopital's rule makes this so much better. Notice the 1/3 came down in front of the first group, times that group to the negative 2/3 power, times the derivative of the inside. And this is why I knew this was going to simplify beautifully, because the derivative of the inside is the derivative of n to the negative 3, which is going to cancel with the denominator when I take the derivative of it. Derivative of n to the negative 3 is going to be negative 3 n to the negative 4 times that negative. It makes it positive there. Derivative of the denominator, obviously negative 3 n to the negative 4. So I know that the n to the negative 4s is a common factor in the numerator and denominator. That can cancel out. Obviously the factors, this 3 and that 3, can also cancel out. I just can't forget that the denominator has a factor of a negative down there. So when I went from this step to the next, I said I did not use L'Hopital, I just algebraically simplified. I said I'm going to have 1/3 divided by a negative. Gives me a negative 1/3. This group is now a factor, and that factor belongs in the denominator to the 2/3 power. And so now I can say, well, can I allow n to go to infinity? Sure you can. Think about why. If n goes to infinity, this term becomes 1 over infinity cubed. Well, that's 0. You'd have 1 minus 0 to the 2/3. That's just 1. So you have negative 1 over 3 times 1 for the negative 1/3. I would say this sequence converges to a negative 1/3.